intermediate position between applications and theory.
Thank you. Thank the organizers for inviting me. And the topic I'm going to share with you today is what we have done in the last few years. I think I started from my career at Texas A&M, and with the second also being my PhD student. She's now working in industry. It's on HB type inclusion problems. And I will follow this outline and try to speed up and finish on time if I could. And the motivation is for composite homogenization, for dealing with the heterogeneous materials. It's very challenging to do. So if we are only concerned with macroscopic behavior, we can go with a homogenized material. So just to evaluate average or overall properties by using the homogenized isotropic material instead of this heterogeneous composite material. So how to go from here to there? We take some homogenization techniques, and which I guess I'll be showing on this slide. Basically, there are a number of methods available, and popular ones based on Ashby's equivalent inclusion method. Essentially, what you do is to replace this heterogeneous material with a homogenized material, which is, I think, has an inclusion shape which is identical. Geometrically, everything is identical, but the material property will differ. So that's something you can design by enforcing some equivalence, either energy or stress or strain. Here I'm showing the Ashby method as equivalent stress. And then you see the key is to know the HTB tensor. Once you have that, you can easily find the Q matrix. So how to get the HTB tensor? I think the next slide I'm trying to review what HTB did in 1957. And he basically was using superposition method as an engineering approach. It just cut it out. There's nothing applied. And no body force, no contact force, and then you cut and then assemble. Because nothing applied here, you have to cancel that traction. So this will be the one you are going to use, and the two is nothing but a Kelvin solution in classical elasticity. Just do superposition, in this case, will be integral over this domain surface. So when you have distributed traction vector, acting as a body force, then you get back to this. It has to, I think, you recover the original problem, which is homogeneous, isotropic, the infinitely large domain containing an inclusion. So that's the problem. But this is based on classical elasticity. We see limitations, and there is no material length scale parameter involved. You cannot capture anything that is depending on the microstructure, including the size effect. So I think that there have been efforts to improve this type of solutions by invoking the high-order elasticity theories. I'll be listing a few on the next slide. Started in 1995, two papers published by this group in International Journal of Engineering Science, and then followed up by a few other people. I think they use different theories: micropolar, microstretch, modified couple stress, and modified strain gradient theory. So we check these theories. I mean, a number of them have been discussed in the last 2 days. I think essentially what we need to be additional material parameters. So at least two additional parameters are involved in each of these theories. So we thought that we may be able to simplify this by using only one additional parameter. That's what we decided to do. We used so-called simplified strain gradient elasticity theory, which contains only one additional material length scale parameter. So we have done a number of studies summarized here. What we have been able to solve. We started off with spherical inclusion in infinite large domain. Then we extend this to finite domain. Then we did a cylindrical, the infinite domain and the finite domain, and the plane strain and the anti-plane strain, and the ellipsoidal. We did only one paper. This is still a challenging problem. If one could do finite domain, it would be very interesting when it's infinite large domain. And then polyhedron and the polygonal, we also did. I think the papers have been published in the last few years. So, but today what I'm going to do is different from what we did for this problem, because this is a single inclusion in an infinite large domain. What we are going to do is coated inclusion, so which means we have 3 phases instead of 2. So I guess the background is that no study has been carried out to our knowledge that was used any high order elasticity theory. But based on classical elasticity, a number of problems, similar problems have been solved. And so we want to extend this by using the simplest strain gradient elasticity theory that's currently available. So that's our motivation. And I guess to put this in context, I just want to use this cartoon to show why strain gradient elasticity theory. And this is classical elasticity theory. You can see if you know the location of that point, you know everything. It's just an assumption made by Cauchy. But for material with a microstructure, and we may need to use a so-called enhanced continuum. So in that enhanced continuum, it is, I think, assumed that the deformation at one material point will depend not only on the location of that point, but also on its neighborhood. So in other words, the microstructure, I think, surrounding that point. So as a result of that, your displacement field will no longer be simply a function of position, and it will be depending on the, I think, what is going on around that point. So your strain energy density function will no longer be a simple function of strain, but it will also be a function of gradient of strain. So that's what I think Mendeleev did in 64 and then simplified in 68 by including strain gradients in the neighborhood of the point of interest. So I will summarize in the next slide what Mendeleev did. So he started off by including second derivatives in the gradient, I think, of strain. You see, ended up with 18 parameters, 16 of them being additional. First two, of course, Lamy constants. Now himself found that theory is quite complicated to use. So he simplified after 3 years, and to just by dropping all second order derivatives, but keeping in the first order derivatives, so that you have 5 additional parameters. And I think they found his, my former colleague, in 97, they just proposed we can even drop more terms and to get this simplest possible form for strain gradient elasticity theory with only one additional parameter C. So that C is positive. I will replace this with L squared later on. You see this is the strain gradient density function. And compared with the Mendeleev's form, you have this special choice of 4 constants. So that's why I think I keep calling this Mendeleev's theory in the simplest form. Okay, so even though different people, I mean, I give credit to Professor Fantis proposed this form. And this is also known to be, I think, a so-called dipolar theory. I'll be showing on this slide. I think thanks to the work by Georgiadis in Greece, and also called first gradient theory of Helmholtz type. I think Professor Marjan was the co-author of this paper. And this slide summarizes basic elements of this theory. So this is starting point. Strain density function. You have this classical terms and then additional terms, with C being the only parameter that is non-classical. I think this L squared, like I said, is because it's positive. And then you have this Cauchy stress, which is symmetric. It's a double stress, it's gradient of Cauchy stress, which is also symmetric. And this is a non-physical stress. It's so-called total stress or equilibrium stress. The equilibrium equation and the boundary conditions will arrive naturally from a very rational process. We, in fact, formulated this in 2007. The other paper was processed by Professor Kiakidis. I think this now gives us some good, I think, the freedom to deal with the macrostructure dependence. So the complicated part is from boundary conditions. The Gaussian equation is, I think, more challenging than the original, the Navier type equation by, the involving of this high order term, but it's more manageable than the boundary conditions. If you look at the boundary conditions compared to the classical ones, it's just much more complicated. The most, I think, a significant point I want to make is, I think, was fourth order tensor. Because this mu itself is third order tensor, the gradient becomes fourth order tensor. It was a nightmare. So we were able to solve 2 problems, but each problem took 80, 90 pages just to find all gradients involved. But I think I will be showing one next. So this is the problem we are going to present today, and the paper has not been published. That's still, I think we're getting ready to submit the paper. And essentially, we have 3 layers. The first layer, phase 1, is a sphere, is radius A and the radius B, and I think the phase 3 is infinitely large domain. So we want to have this problem solved exactly by treating the problem as a boundary value problem, and then after that, I think we want to evaluate Eshelby's tensor by just using the definition provided by Eshelby. Eshelby tensor is a transformation of 4 strains, and then we want to look at some size effect. So here is the boundary value problem we want to solve. The governing equations as just a Navier-like equation. I already replaced C with L squared. And then the boundary conditions, I think we have here the infinity. The infinity we have vanishing displacement, traction, and double stress traction, and the normal component of this gradient of displacement field. But we have 2 interfaces. On those 2 interfaces, we have to enforce the continuity conditions. So we see this in the inclusion phase, and we assume uniform the eigenstrain, so that I think this will be the continuity over the first interface. And these 3 type of boundary conditions were dictated by the general theory, I think based on the variational form of the process, and otherwise we would not know the general form. And on the second interface, it's pretty much the same, except there's a displacement continuity. And the boundary conditions and the interface continuity conditions will help us to get this problem solved. But the eigenstrain tensor prescribed here is arbitrary. So we treat it with all 6 independent components being non-zero, with 0 ones, of course, being special cases. You see, how can we have this problem solved? It's a little bit tricky. But since everything we are dealing with here is linearly elastic, so most powerful tool to use the superposition principle. So that's what we did. So this eigenstrain tensor we decompose into 3 sub parts. For each part we have a uniaxial strain, normal strain, and then the shear strain. And then instead of solving 2 problems, we only need to solve 1. Because the other 2 you can simply achieve solution by rotating coordinates. But for this problem, sub-problem, you still have to decompose. Thank you. And the way you do it, I think that since this normal strain, this shear strain, they decoupled. This is the z direction, that's xy. So you can just simply separate this shear strain contribution from the rest. Then, but the uniaxial, the strain, you have to decompose into 2 sub-problems. One is hydraulic, hydrostatic tension. The other is the vectoric. So it's also called dilatational. And we are going to solve these 3 problems separately, one at a time. So this is the part 1. That's hydraulic or dilatational problem, and this problem is much easier to do because it's uniform. So the solution, the displacement field has to be just along the radial direction with the tangential components I think being zero valued. So the solution has already been obtained and published in this I think journal 2009, and the solution turned out to be more complicated than Lami's solution by these two additional terms. But the solution is available, we will simply use it. So 4 constants to be determined. And we noticed the solution depends on not only the radial coordinate, but also on the material microstructure parameter L. But for the other 2 subproblems are more complicated. This is the configuration we used in solving this problem, I think in 2009. And these 2 are additional boundary conditions because uniform pressure applied, so you do not have to consider double stress traction. And now for the pattern 2, which is the I think the first subproblem for the uniaxial loading, and we see, the second part of uniaxial loading, it's a deviatorical part. And the solution, I think, has this form. We were able to work it out. It took a lot of time. And it happened that we can have this, I think, analytical solution in closed form. So there are 8 constants involved in these 2 expressions. So they were both coefficients of, I think, the radial component, tangential component, and this Legendre polynomial. I think once again we see the dependence on the material length scale parameter. All we need to do is to determine these 8 constants in addition to the first 4 for the first layer, phase 1. So this, I think, in order to use the boundary conditions, you must know traction vector, Cauchy traction vector, and double stress traction vector. We have to calculate that based on the displacement field determined. So this can be done. Once again, took some time to get to this stage. But once we have these expressions, we can simply go ahead to apply boundary conditions. So this is for the pattern 2 and for pattern 3. And this is pure share. Solution form a little bit different from the previous pattern 2. We have, I think, 3 components this time, but it happened that the expressions are identical to those in pattern 2. So that saved us a lot of time. And the parameter theta, theta angle, the phase angle are defined this way. So, especially the theta is between the position vector and the z-axis. So we'll do the same thing to compute Cauchy traction vector and double stress traction vector with all these, I think, coefficients determined in a similar fashion. So I try to speed up. So now, how can you get solution? And we already have this, I think, for pattern 2. This is the displacement field. We are going to apply boundary conditions. First, this is the displacement being finite at the center of the, I think, the composite, and that way we can eliminate 6 constants out of 24 because we have 3 layers. Okay, each layer has 8 constants, totaling 24. So after having eliminated 6 of them, we are left with 18. Then we apply traction-free boundary condition at infinity. 2 will be eliminated further. So we are left with 16 total constants determined. Then we must, I think, use 16 conditions. So we see we just have exact number of 16 conditions to apply. So this first traction continuity, displacement continuity, and then this gradient component continuity. And after enforcing those, and we will end up getting 8 relations here. And another 8 relations obtained from the continuity on the second interface between phase 2 and phase 3. And now we have all 16 equations available to solve for 16 unknowns. It's not trivial, but we were able to solve. For the pattern 3, and pretty much similar, we will end up getting, I think, enough equations to have the unknown constants determined. Once we are done with this pattern, then we have solved the combination of uniaxial, the strain in the z direction, and simple shear on the xy plane. Then we rotate the coordinates, we will be able to get the solution for the other 2 combinations. So that will help us to solve for any problem with a prescribed arbitrary the eigenstrain with all 6 non-zero components. And I think now we can just go ahead to compute the HB tensor according to the definition given by HB. And just simply we will evaluate displacement field and then calculate the strain. And the coefficients will be the components of HB tensor. So that's, I think I just skip, and I think this is the general form. It's quite complicated. It would take pages to write each and every expression. So these are I think the general expressions. And we noticed dependent both on microstructure and position, different from the classical solution provided by HB, which is independent for the position is uniform, but this is not. And this is because the position dependent, we need to do the volume average in order to use the homogenization. So these are the formulas to use. I think I have 2 more slides just show the results. So this is the validation, or to compare with the analytical solution that we had for homogeneous equation problem. It's a spherical. We see our, I think, a numerical solution here obtained is very close to the analytical solution published in this paper. So that gave us confidence. Then we proceeded to obtain some numerical results. As we can see here, it indeed depends on the size. And B is the radius of second interface. A is the radius of first interface. You see, when this ratio is small enough, you have significant size effect. But when this number increases, the size effect disappeared. So it's a localized thing. And I think it's my last slide. I put this up. I thank you for your attention.
Questions? It's not fair. I understood everything, but I must confess I was the reviewer of this paper, so
thank you.
It is interesting the effect which is describing with neatly closed form solutions. I would say that it is a Beltrami-Mitchell equation, not Nami's, but we will start.
Thank you. Thank you.
Some questions?
Professor Forrest? Yeah.
How do you explain the discrepancy, small discrepancy between analytical and numerical solution? What is the origin? How can you get closer to the answer?
It's a very good question. It's possible, but the way we solved all 16 parameters has some, I think, iteration errors.
It was not a finite simulation?
No. And by numerical, I mean the determination of the constants was done numerically.
Okay.
Yes, please.
The eigenstrains are constant within U2.
Yes.
Yeah. Okay.
Special tensor is constant here, or not? Special tensor is constant here, or not?
Is in your solution HB tensor constant?
Oh, no, not constant. Because the strength gradient theory, I think, gives us a non-uniform strength field.